So this time we discussed this, we basically said if we have an incident ray on a medium with a different refractive index, we'll always get a bit of reflection, but we'll also get some refraction. And if you take the total number of photons coming in and the total number of photons reflected plus the total number of photons refracted, the reflected and the refracted beam add up to the incident beam. So light is not created nor destroyed, it's just redirected. It's useful to remember which way around this diagram goes. So I remember that when I have air on top and I have on water underneath, then the refraction goes towards the surface normal, goes from the straight through direction and it's bent towards the surface normal. So that if I'm given a question where the water's on top and the air's underneath, I know that it reflects away from the surface normal by analogy. So the take-home equation is what we call Snell's law. And this is just a very, very, very useful equation. And what it says is, take the refractive index of your first medium, in this case air, and take the sine of the angle of incidence. And take the refractive index of the second medium, in this case water, and then you'll get the sine of the angle of incidence, and they're equal to each other. And refractive indices vary from diamond is a very high refractive index, 2.4, means it slows light tremendously, and air does very little slowing, water more significant, and so on. I don't remember if we did this last time, but which medium does light travel fastest in? Well, N is equal to V vac over V medium. So if I want to know which way does light travel fastest in, so V medium is equal to V vac over N. So the bigger the N, the slower the medium. So which medium does light travel fastest in? Well, you want a smaller N, so water. Light travels faster in water than it does in diamond. Okay? Diamond really slows down light. And then refractive index of material is 2. What are the units for refractive index? Refractive index equals the velocity in vacuum over the velocity in the medium. So what are the units of refractive index? What do you think? No units. It's like coefficient of friction. It's dimensionless, yeah. So refractive index of material is 2. What is the speed of light passing through the material? Okay, so N is equal to V vac over V med. V med is equal to V vac over N, which equals 3 times 10 to the 8 over 2, which equals, what is that? So is it, did you get the clickers? No, never mind then. Is it 1.5 times 10 to the 4? Or is it 3 times 10 to the 4? Or is it 1.5 times 10 to the 8? Or is it 3 times 10 to the 8? What do you think? What do you think? It's going to be 1.5. You've got to divide something by 2. But you don't divide the power by 2. Yeah? So it's that guy. So just watch out for that. Occasionally I will see people and they'll make just a really, I mean, you know, in the friendliest way, boneheaded kind of like math mistake. And you're never sure, is it the day, is it that they're just, their heads are so in the clouds that they're just, you know, they're forgetting some of the simple stuff. or do they have a real, issue, So just sweat the details a bit. In which medium does light have the longer wavelength? Oh, let's have a look. N is equal to VVAC over VMed, which equals, well, let's have a look. V equals F lambda, lambda vac over lambda med. And I want to know which one has the longest, so lambda med equals V lambda vac over N. So the bigger the N, the smaller the wavelength. Bigger the N, the smaller the wavelength. Longer wavelength, that guy. It's so easy to get these seemingly simple questions backwards because, you've got 5 things going. That's why equations come in. Equations are really nice. Equations are our best friend. They kind of they're little safe houses. It's like you're a spy and you're worried about making it from A to B. You go from equation to equation to equation and you know it's right. And so the tradition, frankly, the tradition is we tend to get comfortable with the equations first, even before we really know what they mean. And then with time on task, we get so that they know what they mean more. And then with thought and time on task, our conceptual appreciation deepens. And so historically what we found was people who could do really hard calculus-based physics questions, when you'd push them conceptually, would fall apart. They could do the complicated stuff in the book, but they couldn't answer simple questions. And that came as a bit of a shock to a lot of the teachers, because the teachers would say, my students can answer these really difficult calculus questions, they really know physics. And then you give them a simple project and they won't know what to do. And so there was a bit of a shake-up in the physics community, and people like at Arizona State, Hestonez and people like that started saying, this is not right, we've got to approach this. So they followed on from, if you ever got the book Hewitt was a real leader in this. He basically said, we've got to learn concepts. He was trying to explain physics to a friend without math. And he realized it was quite a challenge, so he really pioneered the idea of conceptual physics. And then the people at Arizona State said, yeah, our best minds don't know conceptual physics when they graduate. So there was a bit of a turnaround, and people really started emphasizing the conceptual stuff. But traditionally, it tends to come at the end. In most people's development, certainly in mine, it came towards the end. And so I think the message is, understand that the equations are great because in a few little symbols they tell you what's going on, but they need interpretation. And that the more you can live with them and the more you can think about them, the better your conceptual understanding will be. And that's important, because when you become a really good engineer, when you got the physics, you got the mathematical dexterity, but you got the conceptual insights. It's like it really makes a difference. So it's a journey you're on. So just recognize there's this conceptual stuff that really is important. So try and get stronger and stronger at it. I want to show you something before I left this, which is how many times, do you remember, you might not actually because you probably were raised around swimming pools, but do you remember jumping into a swimming pool and being stunned by how shallow it was? Probably not, no? I remember the first time I went to a swimming pool, I was 11 years old. I remember getting changed and going down. I was so excited. I was about to jump in the deep end, but I didn't, really know. And I still had my shoes and socks on because I forgot to take them off. So then I was about to jump in. My shoes are still on. So I went back up and got changed and went back down again. And jumped in the shallow end, and it just surprised me a bit. It was like much shallower than I expected. It was deeper than I expected. It looked very shallow, and it was like boom. And there's a reason for that. Did you ever do the thing where you were learning to go underwater, so they'd throw a brick in and you had to dive down and get it and bring it back up? And it's never where you think it's going to be. And what's going on is if you look at a brick at the bottom of the swimming pool, it seems to be like that. And the reason for that is this. I got to backtrack a bit here. Here's you looking, and the light comes from the brick, and it's refracted at the surface, and it is going from a denser medium to a less dense medium, so it is refracted away from the normal rather than continuing in a straight line. It goes away from the normal. And then we interpret light as traveling in straight lines. So you look and you go, oh yeah, it's here because that's the straight line. The straight line tells you it's there. And so you think it's only yay deep. And then you jump in and it's yay deep. Yeah. And I think that's maybe why kiddies have some problems sometimes, because they don't think the water's as deep as it is. So refraction is kind of interesting. So Snell's law, really important. Make sure you know it. Next, some new language: deviation and dispersion. And this occurs with, well, the prime example is with prisms. So why on earth do we care about prisms? We care about prisms because they disperse the light into its different colours. And Newton actually got a huge prism, and he blocked out his room and left a little slit of sunlight coming through. I think this story is made up because I lived in Britain for 18 years, and I can count the days of sunshine on one hand, you know. So it's not as bad as that, but it wasn't particularly sunny when I was there. So you get this beam of light coming through, and then he looked on the wall, and lo and behold, all the different colours of the rainbow. He named the colours of the rainbow. This is, again, the guy's bedrock. And what were the colours of the rainbow? Can you say them? Red, orange, yellow, green. And how do you remember it? So in England, we learn it as Richard of York gained battles in vain, because they killed him at the end. So it's the same thing. So my daughter was in, elementary school, and she comes home talking about the rainbow, and she says, red, orange, yellow, green, blue, purple. And I could feel my stress level go up. Because it's like, oh man, don't know anything. So I got to have a talk to that science teacher, because it's like, she's going to be, set back. And then I started looking at it. I was thinking, what is the difference between indigo and violet? Well, it must be that when you look at the colour spectrum, there's like the red bands there, and there's the orange, and there's the yellow, and there's the green, and there's the blue, and then there must be a big broad band here. So they divide it up into indigo and violet. So I look at the colour spectrum. It's not like that at all. In fact, you can see it here. This is the colour spectrum. And, there's not this big open blue bit, It's like there's the blue, and there's the indigo and violet. And it's like, what's going on here? And so I started reading about it. And do you know why we have indigo and violet? This is one of the most pragmatic scientists, The guy was like, why did he have 7 colours to the rainbow? Well, why? So why do you think 7 is perfection? Why do you think it's a lucky number? Sorry? It's a divine, sacred number in those times in the Roman Catholic Church. So you think, we kind of like poor old Copernicus, if you remember Physics 1, messed up on his sun-centered universe because he had circular orbits, because circular orbits are divine, whereas ellipses are corrupt. And here's Newton inventing colours so he could get 7 out of this thing. And it's just an eerie feeling, isn't it? It's kind of like, this is one of the best scientists, and yet, I think without even really realising what he was doing, he was going towards his kind of like cultural comfort zone, So maybe purple's the right way to go, but the textbook and on the test, Roy G. Biv will do fine, okay? So what happens is that it turns out, although we have refractive index for glass, the question should be, well, which colour are we talking about? Because what we find is that as the wavelength changes, and I'm sorry, so now we've linked colour with frequency, and yet now they're talking about wavelength, because when you're in a vacuum, you can just swap between the two of them and nobody cares. It is frustrating. Sometimes they'll talk about colours in terms of wavelength, sometimes they'll talk in terms about colours in frequency, but it's the frequency that defines the colour as opposed to the wavelength. But what you find is the refractive index changes for a given medium. So this is like up here, so I can't read them, but I can. Crown glass, different refractive index for different colours. And so, different refraction angles. And so if I can get refraction and then refraction again, I can really see this effect. So what they do is they make a shape, this triangular shape, prism, and they deliberately come in at a non-normal angle, and then they come across here at a non-normal angle, so they really get this effect. So what you see is that, the light should have gone in a straight line, but the red and the blue and the violet were spread angularly. This is an amazing contraption. It means that I can break light up into its different rainbow colours, and that's useful. Turns out it's very, very, very useful. So the angle of deviation is the angle between these two rays. And the angle of dispersion is the angle between two rays. And the angle of deviation is the angle between where it would have gone if there was no prism and where it did go. So this is the angle of deviation. It's between the straight through direction and where it actually went. So we say deviation is the angular redirection of a light ray when it passes through a prism. Dispersion is the splitting up of white light into different colours as it passes through the prism. What is this? This is, I don't remember what that's called actually. Anyway, that thing, the angle of deviation is the angle of deviation. It applies to a single colour. Single colour comes in, gets deviated. The angle of deviation is different for different colours, so we get the angle of dispersion. And there's a graphic of it. I am keen that you do study the notes. And I know that all my homeworks are about answering problems, because I see that as the harder thing to do. But I worry that sometimes you just focus on solving the problems. So I'm starting to try and find ways that I give you recall from the notes, because it's important stuff, terminology and the like. And I consider it a gift. But I'm finding out that it's not. With my other class, I found out it's not. So just watch out for that. Do spend some time, and you still have to be able to do the math. I mean, yeah. But don't just put the notes to one side, because we want you to be able to talk like an engineer as well as calculate like an engineer. This is my own little... so this was one of the questions in the back of the book, and I kind of liked it. And why? Because it's kind of like it is a chance for me to kind of like look at some geometry again. It makes you look at geometry again. So what it says is, what's the angle of deviation? I give you the incoming raised angle, I give you the angles in the prism, I give you the outgoing raised angle, and I want to find the angle of deviation. So first of all, you have to be comfortable with what the angle of deviation is, and it's not that angle. That's not the angle of deviation. The angle of deviation is that guy. That's the angle of deviation. It's not even actually on your diagram. Okay? Oh, that's no big deal. We just got to find that angle. So we just do geometry. So what we do, work from the answer outwards. I want to find that guy. To find that guy, I got to know this guy. Oh, maybe you need that guy. Oh no, I give you it. And you got to know that guy. And then you got to know that in a triangle, the sum of the angles in a triangle equals how many degrees? 180. Okay. Well, let's have a look. Let's work our way on yes. If I know this is 150, I know that this is 30. Because in a straight line, we have 180 degrees. So that's 30. And I know this guy down here is 30. So I know this guy here is 120. Agreed? And if this guy is 120, I know this guy here is 60 degrees. Agreed? So I know this guy, I'm given that guy, I know this guy, so I know that guy. And then on this guy, if that's a straight line, and this is a straight line, then that's 60. And if that's, did I do that right? No, that's 60. That's 60. The straight line is there and there, so that's 60. So I have 60 and 60, so what's this guy here? 60, which is embarrassing because it's like they're not symmetrical normally. Okay? So I know this guy, so I know that guy. If I know that guy, I know this guy, I know that guy. So it's not bad. Yeah? If you look at some of my worked examples, I have a much more complicated way of doing them because I wasn't thinking it through. I got the right answer, but it took more work. And then one of my students said, why can't you do this? And it was like, oh yeah, that's how you do it. Anyway, so there it is. Just a little bit of trig, just remind us of it. So why was the prism more than a trinket? How many people here were given a prism when they were a kid to kind of play with? Yeah, a couple. Okay. I was given, my dad gave me a little prism, and I'd look at things through it, and this is like informal science education. It's really important. It's like if you got kids and they show an interest in science, just give them some magnets. Give them a
cannibalize one out of some binoculars.
Yes, a prism. Give them elastic bands. Just give them stuff to play with, and that experience will be really valuable to them. What happens, and it's not particularly any generation, it's just that if you decide you want to go into sciences and you've not played with that stuff, it's not got that same intuitive feel for it. So you got to work harder to get it. So even for yourselves, if you've never messed with magnets, just get yourself a couple of magnets and just play with them, and be like a kid and be surprised, and then say, why is that happening? Because it just makes you so much stronger. So Newton, all right, so prisms were kind of cool because they split light into colors, and people would go, it's a bit like jewelry. They had jewelry at the time, so they knew about faceting crystals and getting these like very colorful little rainbow effects. All right, so that's kind of cool. But why is it still technologically so important? And the answer is really this. We said that E equals HF. And F is color. So what a prism does is, it breaks white light up into its colors, But what the prism also does is it divides photons up according to their energy. There. So I can look at hydrogen and I see a red, kind of peacock green, a blue, some purples. That's very distinct from mercury, which incidentally has a double line, which is kind of interesting, and neon and so on. Very distinct. And these are like fingerprints. If I see that pattern of lines, then I'm looking at hydrogen. Those photons are coming from a hydrogen source. When hydrogen is excited, so it emits light, it only emits light of these distinct frequencies. Now, why is it a line? It's a line because I put a slit in front of my light source to make it really sharp. If I had a light bulb here, I would have a light bulb with a light bulb and a light bulb and then another light bulb, and then over here there'd be a red light bulb. I see what I'm looking at, but to make it nice and sharp, we put a slit there. Okay, that's one thing. Why does hydrogen only emit these colours? Well, that gets us into atomic theory, which sadly you guys don't do much of. And that's just one of the choices that the community's made over the years. It used to be that engineering students would do basically physics 1, physics 2, and then modern physics, where they deal with all this kind of stuff. And then with the pressure that engineering's under to make you more and more productive as an engineer, they started cutting away, so they don't need modern physics. So that went by the board. And if they could cut it back even more, they would do, because it's not that they're mean, it's not that they hate physics, it's just that they're under so much pressure to get more and more really applied courses. Whereas physics people are trying to get the physics majors ready for graduate school, because that's where most people go. Engineers are trying to get you ready so that you can be employed and be useful. So there's a lot of pressure under engineering to make you have useful, very practical, modern skills. Whereas in physics, we can teach you about stuff that's 300 years old and it's fine, you know. So that's understandable, but unfortunately you miss this stuff. So if you get a chance, and it's exciting stuff, it's very interesting stuff. And if you're an EE, or if you're a materials engineer, or if you're maybe a computer engineer, you might learn this stuff. But a mechanical engineer, you might not. And it's a pity not to. So informal education, you know, go and get a simple book on it. Conceptual book's fine, and start reading and just fill in your knowledge a little bit. Most colleges offer a minor in physics. Consider that, although frankly my experience is most engineering majors are so full of courses, you do not really have time. It's possible, but it's a bit of a burden. So, but you can do it informally. Go on YouTube and look at some of this stuff up. It's fascinating. It turns out, as you probably learned in chemistry, there are different allowed energy levels around the nucleus. And they reflect a standing wave. So just as we had a standing wave could have a certain length, and at that same frequency we could have another standing wave that had a different length, and then another standing wave which had a different length. For a given wavelength, there were certain lengths that gave you standing waves. Well, certain circumferences give you standing waves. Oops-a-daisy. And what Bohr basically came up with was this idea that we can imagine the allowed energy levels as being given by circumferences that give us standing waves for the electrons. So the electron is a wave, and the reason why it doesn't dissipate energy is because it's a standing wave. And when you do that, you start getting these certain allowed energy levels, then you can calculate the energy level between them. So if you can get an exciting electron from the lowest energy level to this first energy level, it just absorbs energy, but when it comes back down, it gives off a photon of light with a very specific color. And if it comes from here, it gives off a photon of light with a different color. And if it comes down here, it gives a photon of light with a different color, and there's more and more shells, so you get more and more little strands. And because all hydrogen atoms are the same, they all have the same pattern. So I can look at light coming from the Andromeda galaxy, and I can look at the spectrum, and I can tell you what it's made of. Predominant species that are glowing. And I can identify the chemistry. And that's just like amazing. There's a, if you go on to TED Talks and you look up astronomy, spectroscopy, life, those will get you it. There's a talk by a spectroscopy person who looks at the spectroscopy of stars, and basically is a very entertaining speaker actually. He's quite confident that we will determine if there is life in the universe through spectroscopy. It won't be going there, it won't be shoveling stuff up from Mars. It will be looking at starlight. Because the resolution, both in terms of the spatial resolution and also now in terms of the specular resolution, is such that you can look, and they've identified, it's not even a peak, it's a shoulder on a peak, which is indicative of vegetation. You know, things are green, you know, chlorophyll and all that. There's a shoulder on a peak, which is indicative of vegetation. And he goes, we just look at the atmosphere of planets going around stars, when you can do that now, and boom, when you see that shoulder, you know the grass is green on the other side of the universe. And he said that in 20 years people will find it, and that was about 10 years ago, so it's, you know, coming up. And you can just see it progressing towards it, you know. So this is amazing. Not only that. So I can look across a room and tell you what gas is in that bottle over there by exciting it and then looking at the light that comes from it. But if I see this spectrum for hydrogen and it's got the right pattern, but it seems like everything is a little bit too far to the right. It's the same pattern. It's just all moved too far to the right. That's Doppler shift. That's like when your car starts higher frequency coming towards you and low frequency going away. And if it's too far to the right, I know that it's moving away. And I can tell you that that source is moving away at a given speed, and I can calculate that speed. And I use that to justify the expansion of the universe. So just about all astronomy is spectroscopy looking at light. We infer it all about the universe being 14.6 billion years old, and the solar system being 4.6 billion years. It's all basically from this kind of stuff. So when Newton was playing with his prism, he had no idea that what he was doing, he was playing with a technology which would be valuable for the next 300 years. So what do? We have this little device, it looks like this. Have you seen one in chemistry? Have you seen one of these guys? They're very standard. Basically, it's some kind of telescope which goes from the light source, it gets the light to go in that direction. Then you have some kind of dispersion device, typically a prism, and then we have some kind of, telescope, which then looks and gets you these pictures. In one like this, you'll see one line at a time, so you'll see that, and then you'll move the arm and you'll see that, and you'll move the arm and you'll see that, and you move the arm and you might see those. And you've got to measure the angles manually. Well, why not take the light in and reflect it and bounce it off a what's called a diffraction grating, and that will break it up into its colors and reflect it and send it to basically a photo chip like in a camera. And then I can take all that and feed it into my computer, and I can get that in one, just press a button and you've got it. And with that, I can even have mixtures of elements. And I can deconvolve. I can get peaks which are overlapped. And I can say, let's assume 10% hydrogen, subtract that away. Let's say there's another 50% helium, subtract that away. What's left? And because these things go in very specific patterns for species, I can do math on it, and I can analytically, quantitatively figure out what's over there. And this is getting into the field of analysis, and analysis is like a whole area of science. I did analysis with Rutherford backscattering, interpreting graphs, and then my first job was doing analysis with mass spectroscopy, interpreting graphs. And then I went into electron spectroscopy, interpreting graphs. And then when I was given photon spectroscopy, I knew what to do. So X-ray spectroscopy, there's this whole range of analytical processes, and they're all based on this same technology. And what happens is usually people get involved in one area of it, and they find it's readily transferable. So for example, you want to do this stuff, this really turns you on, you want to be an astronomer, this is what you do. And you'll probably be 40 before you get a job that is full-time. Because everybody wants to be an astronomer. And the competition for a full-time job is miserable. And I'm a surface scientist, and I do this with electrons. The only difference is you're not allowed to use an ion beam to obliterate a planet. But I can obliterate your silicon sample. Do that every day. So I can mess with it. I look at electron spectroscopy, whereas you're looking at photon spectroscopy. And I can move from job to job to job to job to job. I knew a guy who would work 2 years, and then he'd take a year off and go. This was in the 90s. Took a year off, went to China. Took a year off, went to South America. Him and his wife would just work, and then they'd go away. And work and go away. And finally he's talking to me, and I'm going, how can you get a job when you come back? And he goes, I've got skills that people need. And I said, don't they say anything? You got a hole in your resume. And he goes, I've only been ever asked once, and that was my last job. I was gone for it was like 15 months, and the guy said, so where were you for this 15 months? And he goes, me and my wife went to China. And he said, why did you do that? And the guy said, why wouldn't you go to China if you could? And the guy said, yeah, you're probably right. And that was the end of it. It was like, so astronomer, tough time getting a job. Surface scientist, same skill set, pretty much. Same skill set. In fact, I can show you a picture of a surface scientist at work, and I can show you a picture of an astronomer at work, and you cannot tell which one's which. Because they're both looking at computer screens. And the screens look very similar. So just be aware of stuff like that. Okay, so next. How are we doing for time? All right. So when I go from a more dense medium to a less dense medium, my light ray bends away from the normal. Agreed? So, all right. So I start off, and light is coming from. Sorry, I can never find my pen. Light is coming from down here, and it goes out perpendicular, so no angle. And then it comes here, and it bends somewhat. And it comes along here, and it bends more. And it comes along here, and it bends more. And it comes along here, and it bends more. And at some point, it bends along the surface. So it's no longer escaping the water. That's a very important angle. And that's called the critical angle. The angle at which it approaches the surface is called a critical angle. So what we say is that n1 sine theta 1 equals n2 sine theta 2. So n1 sine theta 1, this is my theta 1. I'm sorry, that's very interesting. I never noticed this before. This is n2, and this is n1. Can you change that on your diagram? So n1 sine theta 1 equals n2 sine 90, because if you think about it, that's 90 degrees. Yeah? So you can work out what angle is it that for a given combination of n1 and n2 gives you this effect. And that angle is called theta c, which is the critical angle. The textbook has a different equation for it. It has n1 sine theta c equals n2, but do you need another equation for theta c? I mean, who cares? You can get it from the diagram. So why is this angle so important? Because if I go a smidgen larger in this angle, I get total internal reflection. It goes from going along the surface. If I'm like half a degree more, it all goes back, and there's no light escapes. So I go from light escaping with a little bit of reflection, it's always a little bit of reflection, to all the light is reflected. And this is total internal reflection, and it is better than a mirror. The reason why you went to the binoculars to get the little prisms is because the reason why the binoculars use the prisms rather than the little mirrors, because they could use mirrors pretty much, is that the prisms work better. Total internal reflection is really reflective. So it's used a lot. Today it's used a lot. So the critical angle, know how to find the critical angle and then understand that if you go above the critical angle, you'll get total internal reflection, and be able to pick out which is the total internal reflected ray. And the angle of incidence is equal to the angle of reflection for the total internal reflection. Yeah. I'm going to skip a slide. So this is using total internal reflection. We have a piece of plastic and we have a laser beam, and the laser beam sends in a laser light, and it's totally internally reflected and bounces. And we can use that as a way of entraining light. This is actually cheating. This is doing it with water. You have a Pepsi, or you have some kind of soft drink bottle, and you punch a hole in it so the water comes out, and then you shine the laser beam in, and basically it stays inside the water beam, because of the refractive index of the water versus the refractive index of the air is, If I have the wrong angle, it will escape. Okay? So the trick is you can't approach the wall at too big an angle. And that means you can't bend this thing too great. If you're fine here, but then you come here, you escape. So you can't bend it too much. And the other problem is it depends upon the refractive index of what's on the inside in comparison with what's on the outside. So if I get one of these optical fibers and I put my finger grease on it, I've changed the refractive index of what's on the outside, and I've changed the critical angle, which means I've changed the condition for total internal reflection, and so I might get leakage now because of that fingerprint on the outside. So they tend to clad these, in some kind of opaque polymer, and they know the refractive index of the polymer, and etc., etc. The other thing they can do, which is really clever, is that they use an inner core to the fiber optics, and then they use an outer core, and maybe even an outer core beyond that. So they have the inner core, and then they have an annular outer core, and they do that by basically dipping they'll grow the fiber and then grow the fiber in another material and grow the fiber in another material. So they're changing the chemical composition of the glass as they go out. And what happens with that is that because the refractive indices of these different layers changes, your profile of your light is like that. It never actually hits the surface. So you can basically touch it on the outside and there's no escape. And a guy who's really famous for that is a guy called Nick Dew, who just retired from USF Physics. He was an interesting guy. Nick Dew was one of these old-time professors, really bright. So anyway, so this is kind of technologically really important stuff. You know, FiOS, it's all fiber optics. Revolutionized communication, because when I'm sending signals by voltage pulses and I live in a field, in a world that's full of electrical impulses, interference is all over the place. And copper is expensive and so on. But if I have a fiber optic, it's light. I can chop the light really well. I don't have to worry about inductance. This is the way to go. So you can get a bigger bandwidth with fiber optics, and it's cleaner and it's less susceptible to interference. So this is really important stuff that comes out of basic optics. Let's talk about natural optics, which is basically the rainbow. So how does the rainbow work? And basically we have light comes in from the sun. It goes into a droplet of water. There's refraction on the front entrance. There's reflection on the back entrance. And there's refraction on the exit. And if you think about it, we get red light on top and blue light at the bottom. And yet we have violet light coming out on top and red light coming out the bottom. But when you think about it, you know, what happens is from the top droplet, the red light's coming down here. And from this bottom droplet, the blue light's coming down here. So in our mind's eye, we see it that way around. Blue, red over, red on top. You'll see this on an aeroplane. If you're going through clouds, you can see these things. You see rainbows when the sun is behind you and it has rained in front of you. So in an afternoon, you will tend to see them when you are driving east because the sun is setting in the west. And on a morning, you would tend to see them in the west because the sun is rising in the east. So,
What about double ones?
so double ones is basically when it's particularly dark cloud behind, you get a double reflection. You get basically this mechanism taking place here, and you get that mechanism taking place there. It's always there. It's just usually the cloud is so light that we can't see this because it's so faint. And I'm not honestly sure whether that is kind of like a more complex reflection that's taking place. I don't know. But, you know, I should do, but I don't know. So questions. So which ray displays total internal reflection? Is it 1, 2, 3, 4, or 5? It's 5. And then which ray displays the critical angle? And that's 4. Yeah? Cool. Know those terminology. Determine the critical angle of the interface. So basically what I'm going to say is N1 sine theta 1 equals N2 sine theta 2. And let's have a look. Okay, this is 1.2. So 1.2 sine, that is 90, is equal to 1.7 sine theta c. So sine theta c is equal to 1.2. Sine of 90 is 1, yeah? Over 1.7. And then we just get our calculators out. Did I bring one? I was just grading. So could somebody do that for me, please? Pardon? Oh, thank you. Yeah. 0.71. So what is the angle? So sine theta c equals 0.71. I feel good about that because it's less than 1. So what is the actual theta c? So it's sine to the minus 1 of 0.71. 45.23 watt. Degrees, yeah. So it's okay, just make sure, if you're in radians, just give the answer in radians. If you're in degrees, just give the answer in degrees. Okay. So straightforward. It's just a Snell's law, yes.
So, angle 1 is the angle to the normal?
Or all these angles are measured with regard to the surface normal.
Okay.
That's how I'm going to try and trip you up. I'm going to give you the angle with regard to the surface to see if you use it. So if I was doing a Snell's law, I would do this. I would say that is n is equal to 2. I'd say n is equal to 1.5. And I would give you that angle and tell you that's 30 degrees. In the hopes that when you said n1 sine theta 1 and n2 sine theta 2, you would go, 2 times sine 30 is equal to 1.5 sine theta 2. That's the wrong angle. Because your angle of incidence, your angle of reflection, your angle of refraction are all measured to the surface normal.
60 degrees?
I'm sorry?
60.
So it would be 60. If I told you that was 30, that would be 60. So you have to use the correct angle.
Okay.
I'm going to try and trip you up on that. Slide. Okay. So let's look at, how much longer do I have? 9 minutes. Yeah, cool. Let's do it. You take light, monochromatic light, one color. Take monochromatic light. It's got a certain wavelength. I can represent that by a whole bunch of parallel lines. I have an opening. I often want to collimate light because I find my lens is not so good near the edge. I want my slit rather than a light bulb. So I'm often putting collimators to cut the beam down in size. Here's 3 different collimators. This is a wide collimator compared with the wavelength. This is 3 different diagrams. This is a collimation which is about the same as the wavelength, and this is a collimation which is less than the wavelength. You see that? And for this one, if it's wide compared with the wavelength, all you do is you get like a beam of light going through. There's no light out here. There's no light out there. There's a pretty well-defined beam of light. If I reduce the collimation width, or I make the wavelength longer, either one, and I get of the same order, then I get a bending of the light. It spreads out. That's kind of weird. If I get the wavelength longer than the gap, I get what we call a point source of light. It's as if the light starts here and it goes out in all directions. So we have a door, and we have a person, and you're here, and you're looking. There's the wall, there's the wall, there's the gap. Can you see them? But the light comes in, it just doesn't get bent. Why doesn't the light get bent? Because the wavelength of the light is much shorter than the opening. So we're back here, yeah? Can you hear them? Why can I hear them? I mean, you think the sound would go, I mean, it's, it's going to be like that. The sound will go there, but why would it? The wavelength of the sound is about 1 meter, and the size of the door is about 1 meter. So it begins to spread out. So you can hear round corners, but you can't see around corners. And these are so-called diffraction effects. Well, we're going to get to that. Rays of a given wavelength are straight lines perpendicular to the wavefront. So these are the wavefronts, and those are the rays, if you like. If the barrier opening is bigger than the wavelength of the wave emerges from the barrier as a continuous straight line. If the diameter of the opening is of the order of the wavelength, then the wave spread out in all directions. If the diameter is much smaller than the wavelength, then it can be approximated as a point source. Okay, so we're going to get bending effects when we get edges, and that's going to be a limit for us. This really is exemplified or can be seen and appreciated by Huygens' principle. Back in the day, there was Newton, who was one of the corpuscular people. Light is particles, like little cannonballs. And there were the wave people, and Huygens was a wave person, and they were at each other's throats all the time. And now we know it's a mixture of both wave and particle. Everything has wave properties and particle properties. And so we can construct, using Huygens' principle, which I don't really care that much about, I just like you historically to know about it, but I can construct what happens to the light using these wavelet type of conditions. So I'll leave that for you to look over, okay? I'm going to stop here because I'm running out of time.